All right. So I want to talk about this epoxidation reaction, but I want to look at it from a little bit different perspective. But before we do that, let me just kind of fill you in on a few things. This is I don't know if well, you should have seen by now a journal article before, but this is a journal article from uh, the Journal of the American Chemical Society. This is like the premier uh, this is like the premier journal for uh, chemistry in America. It's probably impact factor. I don't know what the impact factor is, but it's probably the most significant journal for chemistry in the United States and in the world, really, because the American Chemical Society is the largest uh, group of chemists in the world. So yeah. So in with JAX, if you submit a paper to JAX, it's got to be tight, like tight. So this particular paper is dealing with epoxidations. And again, when we talked the other day about synthesis, uh, one of the things that we talked about synthesis being used for is something that we call method development. Method development, right? So method development is exactly that, right? You develop or improve on existing methods, right? So you either develop a new method to do an existing reaction, or you uh, take a method that you already that already exists. Sorry about that. Let me turn this ringer off. You take a method that already exists, and from that method, you improve on it. All right. So this method is an improvement on epoxidation, right? And you know what an epoxide is, right? We talked about the synthesis of epoxides, where you take a alkene and you treat it with some oxidizing agent,
For a U.S. person.
Okay, but then after that, for U.S. person.
right? Treat it with an oxidizing agent, and then from that oxidizing agent, you epoxidize or you generate the epoxide, right? So epoxides are very important uh, chemical moieties, right? Because you can open them, or sometimes you can find them in larger structures. Like when we looked at that natural product, I think it was Taxol, and then we looked at a couple other natural products on Monday. Like epoxides are pretty common functional groups. You find them in a lot of different natural products. So being able to make them is one thing, but being able to make them in what we call, let me add a page right here, what we call an anti-selective fashion is something different. So let me introduce you to a topic real quick. Normally I don't teach this until part two, but it's okay. Y'all are smart. Y'all will get it. All right. So let's say we have uh, a carbon, right? And I'm just gonna put some general functional groups on here. All right. So we have a carbon like that. Right. This carbon. Let me fix these dashes right quick. This carbon is what we call chiral, right? All right. Or we say that it is a stereocenter, right? The reason we say that is because it meets certain criteria. Number one, it's sp3 hybridized. Number two, it's got 4 groups, 4 different groups attached. Right. Number 3 is non-symmetrical. Right. That kind of ties into the sp3 and the 4 different groups. The fact that it's non-symmetrical. And then the fourth thing is a mirror image is what we call non-superimposable. And I'm going to show you what that means in a second. So non-superimposable mirror image. All right, so if a carbon or another atom is chiral, it's got to meet these 4 criteria, right? It's got to be sp3, 4 different groups, non-symmetrical, and the mirror image has to be what we call non-superimposable. I'm gonna show you what that means in 1 second. Let me just rearrange some of this. So you've seen kind of a little bit of chirality already, right? When we show molecules that have dashed lines or when they have wedge lines, that's indicative of chirality or something being a chiral center, right? And so when we take this molecule, I'm gonna copy it right quick. And I'm gonna paste it down here, and then we're gonna draw the mirror image. So take this molecule and we draw the mirror image of it. So here's my hydrogen, and then on the other side I have bromine, and then here is CH3. All right. So those 2 compounds are mirror images, but they're not superimposable. What that term superimposable means is basically I can't lay, let's say A, and let's label them A and B. This is A, and this is B. What the term non-superimposable means is that I can't take B and lay it on top of A and get all the atoms to match up. Right, so that's what non-superimposable means. So these A and B have different configurations, and those configurations are locked, right? So if I took B, let's say I took B and rotated it. I'm going to put an axis through here, and let me know if you don't see it. All right, if I put an axis through here and I rotate around that axis so I could swing that, I'm going to swing the bromine around, right? So it'll match up with the location of the other bromine. And then I'm swing in the process, I'm swinging all of the atoms around except for the one on the vertical axis. Are y'all following that? So let's see what we get. So the vertical axis stays the same. The bromine is going to be here. What about OH and H? What do you think? Is the OH going to be still out front, or is it going to be in the back on the dash? If I'm rotating again,
Would it look like A?
okay, let's see. So I'm rotating this around, so the H is going to be where, or in the location of the BR. So the H actually is going to come here like this, and the OH is going to end up back here. Are you following? I'm taking, so I'm basically putting like a skewer through that carbon bond right here, right? And I'm rotating around that, kind of like you see in Publix, right? Or Kroger or wherever. You're going to see those chickens on the rotisserie. So I'm rotating around that axis. So the H is going to end up in the front, and the OH is going to end up pointed towards the back. Yes or no?
I mean, I see what you're saying, but I still don't get like how the H would be right there.
Okay, so if we're rotating to the left, following?
Mm-hmm.
So you think about a carousel, right? Everybody has ridden a carousel before at the fair, right? So if you think about a carousel, these bottom 3 atoms are your horses, right? So you're going around this way,
Okay, it makes sense.
right?
So it's like they're switching like as they rotate.
Exactly.
Kinda.
Exactly. But you're not detaching them. You're just rotating them in space. So if I took this, I can highlight it or catch it. Oh, come on. So if I took that and brought it over here, let me show you what we mean again by superimposable or non-superimposable, right? Can you see that the BR and the 2 BRs will match up, but the H and the OH will never match up, right? Yes or no?
Right.
Right. And so if that's the case, then we say that those 2 are non-superimposable, right? And we say that the 2 molecules, the image and the mirror image, are what we call enantiomers. Right? Let me write that better. So enantiomers, it's a type of isomer. These are stereo isomers, right? They have the same molecular formula, but they have a different 3D orientation.
So that's what you mean by when you said the H and the OH won't match up, is it because it goes from like the solid to like the dash lines? Like
Yes. And it's fixed, right? It's fixed. You can't take off the H, pop it off, and put it on a different location. The configuration is fixed. So when you look at the image and the mirror image, it's understood that they'll never overlap. So you got the same molecular formula. Let me get this. But a different 3D orientation. Now we're going to talk about the 3D orientation too. I hadn't planned on going here, but I'm kind of glad we are. All right, any questions? All right, so now let's go back up here. And we're gonna do what we call assigning configuration, right? So configuration is gonna be, the configuration is gonna be based on the priority. We're gonna assign priority to each atom, and then we're gonna determine if the configuration is right-handed or left-handed. All right, so the priority is from 1 to 4. Change colors right quick. And it's based on atomic number or atomic mass. All right, so it's from 1 to 4. 1 is the highest, 4 is the lowest, and it's based on the atomic mass. All right, so let's go over here. Which one of these has the smallest atomic mass? Carbon, hydrogen, oxygen, or bromine?
Hydrogen.
Hydrogen. So we're going to call that 4. Okay. Lowest priority is 4. Highest priority is 1. So hydrogen has the lowest priority of all these atoms. We're only looking at the atoms that bonded to that carbon, that central carbon. What about, which one has the highest atomic mass? Oxygen is 16. Bromine is 79. Carbon is 12.
Bromine.
Bromine. So we're going to give that, we're going to assign that a priority of 1. Out of oxygen and carbon, which one do you think? Oxygen is 16. Carbon is 12. So that's 2, yeah? Is that right?
Yes.
Right, because again, you base it on the atomic mass or the atomic number. So if you look at the way that these 3 groups are situated, and you count to 3, because we don't include the 4th group, is 3 going clockwise or counterclockwise? Let's see. So we're counting from 1 to 2 to 3. What do you think? Is that clockwise or counterclockwise?
Counter.
Counterclockwise. So left-handed, right? So this has a left-handed configuration, or we say that is S, right? S is short for the Latin word sinister. And it's counterclockwise, right? Now, the mirror image by default has to be the opposite. The enantiomer is always the opposite of the original image, but we can look at it again too and assign priority, right? Because that doesn't change. It's 1, that's 2, and that's 3. Which way would I count if I'm counting to 3? Which way would I count here? Can you see it? Is that right? Yeah. If I count from 1 to 2 to 3 in order, and I forget 4 because you never count 4, right? That's clockwise, isn't it?
Yes.
Yeah. So the mirror image has the opposite configuration. So we call it R, or Latin short for Latin rectus, or right hand, and that's clockwise. Right. So that's a really kind of a crash course in chirality, but that it'll help you to understand dash lines and wedge lines, because those dashed and wedge lines indicate configuration, and they'll tell you, you'll be able to determine whether or not a chiral center is R, or S, because those are your two choices. It's either going to be clockwise or counterclockwise. The reason that's important is because not every, 99% of the drugs on the market that we take include chirality, some type of chiral center, right? And the configurations of those chiral centers matters because, again, everything that we take has to fit into some type of receptor in the body. So that's why chirality is so important. That's why doing reactions where you can do the reaction and have a chiral product are also important because in the grand scheme of things, those chiral products, when you make them, of course, you're always looking towards a larger goal, right? So you have a method that gives you a chiral product, but then that chiral product is a precursor or a fragment or something to some larger synthetic product, right? We talked about that the other day, linear synthesis versus convergent synthesis. All right, so let's go back up here. You can see right here, right? So let me go to here, right? So one of the things you have to always ask yourself is why somebody's publishing something. I think my screen is frozen. Come on, man. Sorry. Don't tell me the freaking internet went out. I'll tell you what, I could slap this. It's coming at some point. All right. So again, one of the things you always want to ask is why is somebody publishing a work? Why this method? So when you read a paper like this, the first thing you want to do is dissect that first paragraph, right? So the purpose of this paper is usually going to be in that first or second paragraph. All right. So here in the first paragraph, it talks about the history of what we call asymmetric catalysis, or that's using a catalyst to generate products that have chiral centers present, right? And it says two of the most significant developments were sharpless epoxidation, right? And the application of those to kinetic resolution. We're not going to talk about kinetic resolution, but the sharpless reaction is shown up top. Can you see that? The chirality that's generated because of this right here. This titanium isopropoxide and diisopropyl tartrate. Those two things make a chiral catalyst, and that catalyst it catalyzes the reaction, but it also does it in a way where the epoxide comes out chiral. Can you see that on each one of these carbons here and here, those are chiral centers? Do you agree? And the criteria again for chiral center is that the carbon is sp3 hybridized, that is not symmetrical, that it has 4 different groups on it, and then that the mirror image is non-superimposable. All right. So let me ask this question. I think we can fit it in down here too. What would the mirror image of this product look like right here? So let me see if we can. That's the epoxide, yeah. And remember, the mirror image is the exact opposite of the original. So instead of a wedge here, that would be a dash. And then instead of R2 being on a wedge, it will be R1. And then R2 would be here on a dash, right? These two are mirror images, and so we call them enantiomers. Right? Enantiomers. That's bad syllabification, but sorry about that. So R1 ends up here. And then R2 ends up on the dash. Are y'all following? Yes or no?
I get what you're saying. I think it's just being able to like see what this would maybe look like in the 3D form. That would
In
help.
3D, you said?
Yeah, like that would be more visually.
Okay, we can do that. Let me grab the other example, and then I actually have a program where we can do 3D. And I'll build that exact same. As a matter of fact, let me just do that now. It might take me a second to build it, but I can build it real quick. Because the chirality definitely is dealing with the 3D orientation, all right? But it's everywhere. Like there's no drug on the market except for maybe Tylenol, which is acetaminophen, right? That doesn't have a chiral center somewhere. Right? But the point of the paper is they are trying to innovate. They want to. Oh, this thing keep freaking freezing up. Let me share it again. Yeah, what they're doing is innovating an existing reaction. Right, so that sharpless reaction, what they're publishing is a way to do it better. Right, and I'm gonna show you that in that second paragraph, and I'm gonna show you their method and what they're able to do, and then I'll show you the 3D part. Right, so right here again, first and second paragraphs of any paper are gonna give you the rationale why we're doing what we're doing and what we're doing. Right, so right here, here's the reason for their innovation, or the reason for their publication. Despite the enduring success of sharpness, kinetic resolution, there remain significant limitations. And then boom, in this communication, we disclose a method to address these limitations. So this is a method development paper that deals with improving the outcome of epoxidation reactions. And then they tell you what they've done. We've developed highly enantioselective and diastereoselective method, a highly enantiomer diastereoselective method to synthesize acyclic epoxy alcohols with 3 stereocenters and good to excellent yields. That's the whole paper in a nutshell. Everything else is just a technical part of that, right? But their method is shown over here, right? So they take an aldehyde and they add a zinc nucleophile to it, and then from that they're able to epoxidize using this oxygen gas and one atmosphere, and then titanium isopropoxide as the catalyst. Right, so it's a very simple methodology. And then in their optimized reaction, which is shown down here, it's the same reaction, but now they do it with a chiral catalyst, right? Or a chiral ligand 2, which is shown here. So basically, when you look at this ligand, what it does is it attaches itself, because you know nitrogen has lone pairs. If we put them in, And so that ligand can bind to titanium, right? And form what you call a complex. So you'll have a titanium with nitrogen here, and then nitrogen here, right? And so that complex is what catalyzes that reaction. Right? It's very that's a whole nother topic though for another class. But the point I wanted to make was that they're able to make these epoxides in really high yields, and you're setting 3 stereocenters, which is not trivial, right? Each one of these carbons right here, 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 and here is a stereocenter. That's not trivial at all. To set 3 contiguous stereocenters like that is not trivial. It's actually very difficult to do. All right. So let me show you a table right quick in here, because they'll have they always include the scope of the reaction. So look at this table and look at the different substrates that they're able to generate, right? All this different functionality. And I want to talk about a couple things. Number one is the percent yield, which is not listed in this table. God dog it. Oh, yes, it is. It's in parentheses. So 60%, 65%, 90%, 81, 96, and 96 is the percent yield, right? And then the other part is right here where it says percent EE. Right, that's what you call your enantiomer ratio. Right, so 93% EE right is the same as saying like 100 to 7, right? Something like in that area, right? So you have 93% EE for this compound. So this enantiomer is formed in 93%, and then the mirror image is 7% because it has the total up to 100, right? Same thing here. You get that in 96% EE. So 96% of this, 4% of the mirror image, right? And that is anything above 90 is considered excellent as far as organic chemistry is concerned, right? So this 93 and 96 and 99% EE, you can't beat that. That's like the gold standard for enantiomeric excess. All right, so that EE again is that it's a abbreviation for what we call enantiomeric excess. So what I'm gonna do, if I can get this to work, I'm going to let me see if I can open an old file so I can keep the same settings. I'm gonna build that, and then I'm gonna try to put it in 3D. Build one of those and then put it in 3D if it'll open. All right. Anybody got any questions while I'm doing this? All right. Let me do something real quick, and then I'm gonna share my screen so you can actually see what's going on. Change. So this is a program called Chemdraw, right? So when I'm making tests and things like that, this is what I use to build the structures and whatnot. So let me take this structure right here. I'm gonna make it dash like theirs. And it's here. All right, and then this is This OH is on a wedge. Like so. So that is the main enantiomer. And then I'm just going to cheat and copy it and paste it. The mirror image of that would look like this, where everything that's wedged becomes dashed and everything that's dashed becomes wedged. Like that. Now let me see if I can get this into 3D. Where is it? So I can get them both in 3D. I think it'll pop up in a different window. And then you'll be able to see like the differences in the configuration. Oh no. There we go. So let me zoom in on that. Oh, I need to be able to rotate it. Hold up. So note that there's a function on here where you can act. There we go. This is what I want to show you. So can you see the epoxide? Let me zoom in. So this is this one, right? Where the epoxide is going pointed back and the alcohol is pointed up. So can you see that? You see the epoxide here? Do I need to zoom on that?
I can see it.
Right, and you can see the epoxide here has a different configuration than the alcohol here. Right, now let me show you the other one. Right here. Uh-oh, didn't try to do that. See if I could get that one to come up. All right, so here you can see the difference in that one too. You see how the OH and the epoxide are kind of on opposite sides? How one is kind of right there. See how the OH is pointed out on the wedge and then the epoxide is kind of pointed back. Right, so that makes a huge difference when you talk about biological activity, when you talk about biological activity, when you talk about a molecule fitting into a specific receptor in the body, that chirality matters, right? And so when you can do a reaction and get one enantiomer favored over the other in a high number, like 99% yield, 99% EE, that's a golden, yeah, that's like what you want, right? That's a very desirable outcome. All right. Any questions about anything? Let's see if it'll come up here. So here you should be able to see. I should delete this. Yeah. So you can see the difference in the epoxide and the alcohol. Let me take this out too. Sorry. And you can see in the enantiomer right here, you see how the alcohol is going in a different direction than this alcohol over here. Right. So all of that matters. It matters in the grand scheme of the application of these products and what you're going to use them for. So that being said, I'm gonna stop right here and I'll take questions. Any questions? All right, no questions. Okay. All right, we're gonna stop here. Remember, Friday, no class, but the exam is Friday, and it'll be posted at class time by 10:30. I mean, 11 o'clock. Sorry.